So in this last screencast of chapter 1, we are going to talk about functional groups and biochemical molecules. Functional groups are one of the most important things that you need to know in organic chemistry because it'll help us group molecules into different reactions. And so later in several chapters, we'll say things like, well, aldehydes react this way. And if you don't know what an aldehyde is, you're going to be in trouble. So I really suggest spending a little bit of time and really making sure you understand these functional groups. So let's define functional groups. We talked about them a little bit in general chemistry, but I just want to review that for just a hair. So functional groups are just specific arrangements of atoms connected by specific types of bonds, and they tend to react in a characteristic way. So this is one of the times where I love how something in science is named. These are functional groups because they function, they're reactive. So these structural components are called functional groups, right? And the molecule's reactivity is really governed by these functional groups. And each functional group has its own name. Now, one of the things that people disagree on is whether alkanes are really functional groups or not. Because alkanes, by and far, really are very unreactive. But we still need a way to classify a molecule that just has carbon-carbon and carbon-hydrogen bonds. So if compounds just have carbon-carbon and carbon-hydrogen bonds, they're called alkanes. And we have some examples of alkanes here to the right. So methane is the simplest alkane. We also see a branched alkane, which is 2-methyl-octane, and then a cyclic alkane, which is ethyl cyclohexane. Now, one of the things that are interesting here is because these only have carbon-carbon bonds and carbon-hydrogen bonds, their properties are going to be really similar. So let's talk about that a little bit. Alkanes tend to be among the most unreactive organic compounds. And so for this reason, if you have liquid alkanes like pentane or hexane, they are often used as solvents. Because when you do a chemical reaction, right, we have two things that react, but we need some way to disperse those molecules. And so to do that, we use solvents. And so we want solvents good solvents don't react because we don't want any side products in our reactions. And so alkanes tend to be really good side products. Now, why are they relatively unreactive? Well, they're relatively unreactive because the carbon-carbon-hydrogen bonds are so strong. So they are unreactive because the carbon-carbon and carbon-hydrogen bonds are so strong. So when we think about reactions, I want to remind us that during a reaction, bonds have to break. So if carbon-carbon and carbon-hydrogen bonds are among the strongest single bonds that we're going to encounter, that's why they are the most unreactive. Alkanes also tend to be unreactive because the carbon-carbon and carbon-hydrogen bonds are either non-polar or only very slightly polar. And so we're just going to go ahead and say non-polar, right? And so there's no difference in electronegativity between those atoms. Now, in chapter 7, we're going to explain that a large driving force of a lot of the chemical reactions that we look at depend on the existence of these bond dipoles and bond polarity. And so that's one of the reasons that alkanes are really nonpolar. Now, organic molecules having atoms other than carbon and hydrogen or bonds other than single bonds tend to be a lot more reactive than alkanes. So carbon-carbon double bonds, for example, are really reactive. In some cases, this is due to the introduction of weaker bonds, right? Like double bonds. Or to the presence of large bond dipoles. So as you're going to learn through the book, the specific arrangement of atoms connected by specific types of bonds tend to react in those characteristic ways. And even though such arrangements may consist of only 2 or 3 atoms, they're super important because they dictate the function or the chemical behavior of the entire molecule. And so those structural components are so important. So we're going to look at a couple of them. So here are some common functional groups. You need to commit these to memory. What you're going to see when you look at this table is the compound class, right? And we can kind of view that as the family. And then what structural component identifies it as the compound class? So for example, alkenes have a carbon-carbon double bond. Anywhere in the molecule, we got a carbon-carbon double bond. All of a sudden, that's an alkene, right? So it's no longer an alkane, it's an alkene. And so what you're going to see here, here's just some overall comments about this, is that functional groups, right? So let me put up here, functional groups can be distinguished by, one, the types of bonds they contain, or 2, they can be distinguished by different types of bonds. So, for example, when we talk about the bonds they contain, if we look here at an alcohol, we're going to see that an alcohol has lots and lots of carbons, but what really makes it an alcohol is this carbon OH bond that's shown here in red, right? Another example would be like a thiol, which reacts in a lot of similar ways to alcohols, where they've got this 8SH bond right here, okay? And so those are some things that distinguish functional groups. Now, one of the other things I want you to notice is some functional groups contain the bonding arrangement of smaller functional groups. And so this can be a little tricky sometimes because, for example, if you look at an alcohol and you're like, alcohols have OH, I want you to notice over here that a carboxylic acid also contains an OH. So you have to look at what's next to the OH to see this C double bond O. Now, the C double bond O just by itself will refer to quite a lot. And you'll see it referred to a lot of times as a carbonyl, right, group. And so we'll say, look, there's the carbonyl group of a carboxylic acid, and we're honing in on that C double bond O. Notice that the C double bond O group shows up through a lot of different functional groups, right? Ketones, aldehydes, carboxylic acids, esters, and amides. And so it's kind of a frequent flyer. So that's a pattern that we really need to distinguish. Also, I want you to notice that rings don't generally constitute new functional groups. In most cases, the reactivity of a functional group that is part of a ring is really similar to its reactivity of an open chain. There are some exceptions, though. Notice that arenes, right, are going to be discussed pretty in depth in chapter 14, as well as some later chapters. And we'll get to that in organic chemistry too. But an arene, we also can know as an aromatic compound. We've got alternating single and double bonds here, right? Then I want us to note another example is an epoxide here. This is a ring with an oxygen group, and it's a 3-membered kind of ether. Those tend to be really reactive. We'll discuss those in chapter 4. This ring is really highly strained, which tends to make them more reactive. So we're going to talk about ring strain, but they're so reactive a lot of times they'll explode, and so we have to be really careful with those. You're also going to notice here a phenol down here, and so what this is really starting to introduce is we can have some specific new names when we have groups off of arenes. So if we talk about a phenol, you need to know, hey, look, this is a ring with alternating double bonds, but it also has an OH group here. Now, there are 2 conventions that are used in this table to represent generalized structure. One is the abbreviation R, okay? And we can just imagine that R equals the rest of the molecule, okay? And that's one of the conventions that we can think about. The other, and the other thing here is, I want you to understand, is R here indicates an alkyl group. And so that can be just a carbon chain of any length. Okay, and so that's just a generic thing. And the absence of an atom at the end of a bond indicates there's either an R or an H may be attached. So what we're looking for here is, notice there's nothing at the end of this bond, and that says, hey, look, you can either have a hydrogen here or an R group. It's not going to affect the reactivity. Where it does affect the reactivity, for example, is here between aldehydes and ketones. Aldehydes are going to have a hydrogen. Ketones are not. They're going to be in between two R groups. And so those are some just pretty normal conventions that we're going to see. And we'll talk more about some conventions as we go on and look in Inner Chapter A. Now, the chemistry of living cells is ultimately really the chemistry of organic compounds. That's why if you're a biology major, you are taking organic chemistry. So organic molecules are exclusively found in organic or in living organisms, and they are called biomolecules. If you are going to go on and take biochemistry after this, you will focus on living organisms and biomolecules, and you will focus in on the four classes of biomolecules. So you'll focus in on proteins, carbohydrates, nucleic acids, and lipids. And so those are the four things that you'll focus on. So in this section, what we're going to do is we're going to introduce proteins, carbohydrates, and nucleic acids, but we're going to leave the introduction of lipids to chapter 2, particularly section 210. So you should see that. Now, this organization has been chosen because proteins, carbohydrates, and nucleic acids have a common attribute, right? So proteins, carbohydrates, and nucleic acids have common attributes. They're typically very large. So they have these really large structures that are constructed from a relatively few type of small organic molecules. And so a lot of times what we say is, hey, look, these guys are biopolymers. So polymers have these repeating units of monomers, which are these small molecules. Now, by contrast, lipids are going to be relatively small to medium size. And are characterized in a different way. So these guys are really characterized by their repeating units. Here, lipids are characterized by their solubility. And they are mostly insoluble in water. And so that's what we see as far as lipids are. The small organic molecules that compose the large proteins, carbohydrates, and nucleic acids are recognizable. They're building blocks that have distinct structural features and characteristic functional groups from table 1.6. So we're going to see these functional groups come back. If you can kind of imagine, these small molecules that repeat are kind of like Legos, and you can arrange them in different ways to make larger structures. So we're going to review some of these characteristics in the remaining parts of these chapters. So we're going to talk about proteins, carbohydrates, and nucleic acids. So proteins, right, are really highly versatile molecules. And so we have some examples here. So when we think about proteins, a lot of times we think about muscle tissue, which is shown here. But basically, if we start here at your muscles, right, when we think about proteins, we think about muscles. We have like this typical fibrous protein. Okay, so it forms fibers. And we can even zoom in and we can say, hey, look, there's a segment of a protein and it's made up of small amino acids, right? And so we can look at everything from these molecules, and then we can go even smaller and say, okay, what functional groups are found in amino acids? So proteins are made up of amino acids, okay? And so there's several kind of important functions that we see. The specific proteins actin and myosin are responsible for the mechanical processes involving muscle tissue. Right? Another type of protein, which is cortactin, right, regulates cell shape. Right? And my favorite type of protein, I get all jazzed out about these. There are proteins that are classified as enzymes. Now, not all enzymes are proteins, so that's just something to be aware of. But a lot of our enzymes are proteins, and they act as catalysts for biological reactions. So they make the magic happen. Super, super interesting. So proteins are constructed from a few different types of small molecules. We've already called them amino acids. So I want us to look at the features of amino acids. I want you to notice here, this is an alpha amino acid. So all alpha amino acids have the same basic structure, and that's shown in black. What they differ, though, is the identity of the side chain here, right? So all alpha amino acids have the same basic structure, but differ in the identity of the side chain. Okay. Now, I want you to notice that an amino acid, and I love the name amino acid because it gives us a clue of the functional groups. So amino here kind of reminds us of an amine functional group, and you're going to notice we have an amine functional group there. And then the acid part references the carboxylic acid. Then, so on one side of an amino acid, we have an amine. On the other side, we have a carboxylic acid. And in between connecting these is a carbon, and this is called the alpha carbon. It's called the alpha carbon because it's just one over from this carbonyl carbon. So there's the alpha. If there were two, it'd be beta, and so on and so forth. But they never will be. There's always just alpha. And then off of the alpha carbon is where we get the side chain, and that's called the R group. And depending on what that R group is, that R group can contain all sorts of different functional groups and can really drive the functionality of a protein, which is super exciting. So we have 20 naturally occurring amino acids. When you get to biochemistry, you'll see that there's a few other, I like to really say these are the 20 most super duper common naturally occurring amino acids. And what you're going to notice is the side chains of the amino acids is what distinguishes one amino acid from another. And so we have these 20. Now, I want you to notice that these side chains of amino acids can be polar or non-polar, and they can be acidic or basic. So we can use what we already know about general chemistry and say, hey, Dr. Pierce, I remember if things were just carbons and hydrogens and that's all they are, then they're non-polar. Well, it's really easy to identify things that are non-polar side chains, amino acids, right? That's non-polar, it's just got carbons and hydrogens. That's non-polar, it's just got carbons and hydrogens. That just has a hydrogen. That's non-polar. This is non-polar, it just has carbons and hydrogens, carbons and hydrogens, carbons and hydrogens. This is non-polar and it's mostly carbons and hydrogens. I know there's an amine here, but it does get classified. This just has carbons and hydrogens. This is a super interesting one. What you're going to see is the ring will actually become part of the peptide or protein backbone. So that gets to be really interesting. And then what we see here is methionine, but we've got two R groups there and it tends to make that non-polar. So we are going to revisit the properties of proteins greater in depth as we talk about biomolecules. So we'll talk about these in individual chapters. Here are polar, acidic, and basic. I want you to notice that the acidic amino acid side chains are both carboxylic acids. So if you can recognize that functional group as carboxylic acid, you already know how to classify those as acidic amino acids. Basic amino acids are going to contain these nitrogen molecules, either these terminal ones or this one in a ring. Methionine, of course, is the exception. But understand, amines in organic chemistry tend to be basic. So if you can remember that, then you can see here that these will be basic. Then we're going to have polar amino acids, and you just have to remember that polar is a difference in electronegativity. So notice here, anytime we introduce a heteroatom like oxygen, right, that makes that very polar. And so we see, and then we have like these oxygens, these carbonyls, right, that also makes it polar, and then cysteine tends to be polar. So again, we'll revisit some of these as we go through the rest of our book. Now, let's talk about carbohydrates and monosaccharides. So carbohydrates in an older language are also known as saccharides. And they serve in just this really variety of biological functions, right? They are fuel for metabolic pathways. So when you get to biochemistry and you start talking about metabolic pathways, you're really going to focus on carbohydrates because they're a large part of that. They're the structural component of cell walls. Right? So for example, cellulose. Right? They participate in the blood clotting process. And they also regulate the immune system. Okay, so these are generally characterized by their chemical composition. They're composed only of carbon, hydrogen, and oxygen. What you're going to notice is there's 2 hydrogen atoms for every oxygen atom, regardless of how many carbon atoms are present, giving each carbohydrate the general molecular formula of CX H2Y OY. Okay? And so what we can see here is sometimes the oxygens, we're looking at monosaccharides, so what we're going to see in monosaccharides is the number of carbons and oxygens match. When we get into disaccharides, that won't happen anymore, polysaccharides. But what will always be the case is there's going to be 2 times as many hydrogen as oxygen atoms. Now, as I've already mentioned, carbohydrates are frequently large molecules called polysaccharides. It'd be helpful if I could spell that. I always have to think about it. Right? And these have 10 or more monosaccharide units. You can also have something called oligosaccharides. These have 3 to 9 monosaccharide units. You can have disaccharides. These have 2 monosaccharide units. And then, of course, monosaccharides are just 1 monosaccharide unit. And as I've already mentioned, in monosaccharides, the number of oxygen atoms is the same as the number of carbon atoms. And so you get this general formula CX, H2X, OX. But again, that's only for monosaccharides. Once we get into disaccharides and polysaccharides, that number changes a little bit because we end up with some linkages there. So let's talk about linkages just a little bit here as we talk about the size hierarchy of carbohydrates. So we're going to start here with monosaccharides. These are really, really small molecules. And what we're going to notice is they have an open form, but they have a chain form. In their chain form, the way to recognize something is a carbohydrate is the oxygen is part of the ring. Okay? So one of the kind of fun questions that people tend to give is they'll show a ring with a lot of OHs off of it, and they'll say, hey, is this a carbohydrate? Is this a monosaccharide? And unless there's oxygen part of the ring, the answer to that's no. So that's one of the easy ways to identify if something's a monosaccharide. Now, notice these monosaccharides link up to form disaccharides. They do this through an oxygen bond here. You're going to see brackets here and an N and then a line and squiggles. The N here means we've got some repeating units for this polysaccharide, and so it's just telling us that, hey, these two things repeat over and over and over again. Then and so that's kind of what these squiggles show. Now, when we look at this, here are some of our larger organized structures, such as those found in cellulose, which makes up, of course, cell walls in plants. Now, let's talk about kind of our final biomolecule that we're going to talk about in this section, which are nucleic acids and nucleotides. So what we see here, right, is we have some chromosomes, but what you probably will recognize kind of off the bat is this double helical DNA, right? And so when we have a pair of intertwined nucleic acids, they are going to form the double helical deoxyribonucleic acid, which is DNA, which stores genetic information, and a single nucleic acid chain, of course, forms RNA, right? So DNA has 2, RNA has 1. Now, nucleic acids are constructed from really, really small molecular units called nucleotides. And so you can see here are nucleotides. And I love this because it shows the organization, right? We have chromosomes, which are found in cells. Chromosomes are made up of DNA. DNA is made up of nucleotides. Now, let's look at some features of nucleotides. So we can break nucleotides into kind of 3 distinct components. When we look at these 3 distinct components, the first component is inorganic phosphate, right? And that's that OPO3 group, okay? And they're showing you that kind of here in green. There's your inorganic phosphate. The second thing is a cyclic monosaccharide. Okay, that's a sugar. So one of those carbohydrate pieces. And you can see that there. Again, there's that oxygen as part of the ring. So we can identify that as the cyclic sugar. It is, when we talk about DNA, what we're going to see here is the cyclic sugar here is DNA, and the cyclic sugar is called deoxyribose. Deoxy just means that D prefix and the oxy means we're lacking in oxygen for ribose. When you talk about RNA, that's ribonucleic acid. And so ribose is the sugar just as is. So look at the comparison between here and here. You're going to notice in this 2 position here, there's an OH when it's ribose. And then deoxyribose means it's missing 1 OH. And that is right here in this number 2 position. So that oxygen atom is missing. So, but those are the 2 that we see in RNA and DNA. And then nitrogenous bases. Okay, and so let's talk a little bit more about these nitrogenous bases. In RNA, there are 4 nitrogenous bases, uracil, guanine, adenine, and cytosine. You can see these are abbreviated as U, G, A, and C respectively. And then in DNA, the 4 nitrogenous bases are G, A, C, and T, which is thiamine. And so you can see these. One of the things that you're going to notice is in the DNA double helix, the guanine pairs with a cytosine. So we've got G and C. And then the adenine pairs with the thymine, which is A and T here. How I like to think about it is the things that are curvy, the G and the C pair together, and the things that are pointy, the A and the T pair together. And so these are the things that pair, but what you're going to see here is a double ring will pair with a single ring each time. Now, you're going to notice that DNA has thymine while RNA does not. It's got uracil, and so that has been replaced there. So this concludes kind of our introduction to functional groups and some of the biochemical molecules that we're going to see. This also concludes our screencast for Chapter 1.